Good afternoon, everybody. Welcome to a cloudy, cold day before Thanksgiving, Chem 170 with your host, me, Dr. White. Thank you for coming. Sometimes attendance before Thanksgiving as well. It's before Thanksgiving. All right. Good afternoon, everybody. All right. Important information. First of all, on Monday, I will not be here. I will upload by Sunday a video for what I would have covered on Monday if I'd been there. I'm going to have this side taken care of, new cataract surgery. This one's doing really good. Thank you. And thank my surgeon, Dr. Caban. But anyways, that's one thing. A week from today, after class at our lab, I will send out an email with the password for test number 4. Sometime between now and Friday, I will post and send out an email. Excuse me. I will post and send out an email, important information, test number 4, and you'll find out there's a lot more, what do I call it? General information or just whatever I call it. Why? Because if I ask you, is my left hand chiral or not? It's chiral, but that's not reactions. Oh, general knowledge, that's the term I was searching for. It's not reactions, it's not nomenclature, it must be general knowledge. And if I ask you to draw the enantiomer or something, that's not reactions, that's not nomenclature, so that's general knowledge. And that's the reason why you'll see for test number 4, when I post it, there will be a lot more general knowledge points. And like I said, I'll post that on by Saturday morning at the latest, hopefully, maybe even to probably sometime Friday morning. I'm going to take tomorrow off. But anyways, that's one thing. The other thing is, since I'm giving a test next Wednesday and I won't have office hour next Monday, I'm going to still be out of it like I was last time. I will have a special office hour on next Tuesday. If you have any questions, I'll send out I'll put that in email too. So with that, let's get going. What I want to do today first is go through the fats and oils or lipids problem set. All right, thumbs up, people. Do you see the lipids practice? Thank you. All right, you can tell it's getting to the end of the semester. Dr. White's getting real lazy. What's the lipid? C notes. Thanks, Dr. White. Oh, that's me. Anyways, what's the lipid? It's a chemical obtained from something alive that's not soluble in water, but is soluble in nonpolar solvents. Now, name one type of a lipid. Well, a fat is, an oil is a lipid, and a steroid. Those are all lipids. You should know what's the difference between a fat and an oil. A fat is a solid or semi-solid at room temperature, and oil is a liquid at room temperature. If you want to put down to what is room temperature, 25 degrees C, that's okay. If you don't, that's okay. Remember, I'm this close to the greater me. All right, now you should know what is yellow grease, pig's fat. Well, I don't have it down here, but you should know white grease. What is that? It's not named after me, but, oh, that was a bad joke. As pig's fat, you should know what is tallow, beef fat. Now, let's look at some reactions. Give the organic product or products for a following reaction. Now I have this big molecule there. It's a pseudo fat or oil. And the question is, when you react it with sodium hydroxide and water, what happens? Well, you should know in fats and oils, the key functional group is an ester. And there are three of them, 1, 2, 3. And here I have written for fats and oils, the ester written a little backwards, but it helps because this is how you write fats and oils. My software does it. I do it even without software. Remember, I worked in this industry. And ester, base, water, you get back the alcohol you would have used to make that ester, plus not the carboxylic acid, but the carboxylate anion that you would have of the carboxylic acid you would have used to make that ester. Now, if you notice right here, there's a double bond. I don't know of a reaction of sodium hydroxide and water in a double bond. Do you? No, because they're not. So that won't be affected. So first ester, this alcohol, this carboxylate anion. Remember, do you break carbon-carbon single bonds? No, and you don't. You'll get it wrong. Next ester, you get this alcohol plus this carboxylate anion. And the final ester, you get this alcohol, which means you get glycerin plus this carboxylate anion. Now for B, same starting material, but now I'm reacting with H plus, and you should know if I put HCl there, that's also H plus, because HCl, hydrochloric acid, is the acid in your stomach that breaks down fats and oils, along with water. And what you have is acid hydrolysis of an ester. You get back the alcohol and the carboxylic acid you would have used to make that ester. And for this one, do you know reaction of acid and water under these conditions that will affect that double bond? And the answer is no. I didn't go into reaction conditions, but to actually acid and water to a double bond like that, you really have to heat it to high temperatures. And here, first ester, you get this alcohol plus this carboxylic acid. The double bond is still there. You break carbon-carbon single bonds. No. And second ester, you get this alcohol plus this carboxylic acid. And third ester, you get this alcohol, so you get glycerin plus this carboxylic acid. Now here, I have this molecule now reacting with hydrogen nickel. I'm being sneaky. I can do that sometimes. And the first question is, what functional groups are in this molecule? Well, there are 3 esters and a double bond. Will an ester react with hydrogen and a catalyst? And the answer is no. Will double bond react with hydrogen and catalyst? And the answer is yes. You learned that for test 1. Double bond, hydrogen catalyst. Catalyst can be nickel, platinum, or palladium. You break the pi bond, and each carbon of the double bond gets a hydrogen. So these esters are not affected. And these R groups are just carbon-carbon single bonds are there. The only change, notice to help you out, I said, look, and that is you break the pi bond right here, and each carbon gets a hydrogen. You could have written that CH2, CH3, but you don't have to. And here, all I've done is change the catalyst. And now, if we look at, E, we have that same triglyceride reacting with steam. What's steam? Hot water. And what's the 2 ways you can make a reaction go quicker, which is always a good thing, especially when time is money, is 1, use a catalyst, and we've done that with base and acid. The other is, there's a rule of thumb. Can you see it's written on that thumb? And that is, for every 10 degrees Celsius, you increase the reaction temperature, the reaction rate, how fast it goes, doubles. So if I don't want to use a catalyst, I can use steam, which is very, very hot water. It's high pressure steam. And when you take an ester and react it with steam, you get the same products as if you had acid hydrolysis of an ester. You get back the alcohol, the carboxylic acid you would have used to make that ester. Now, will steam react with a double bond? No. So first ester, I get this alcohol and this carboxylic acid. Second ester, I get this alcohol and this carboxylic acid. And third ester, I get this alcohol glycerin plus this carboxylic acid. Now here, I get a little sneaky. Again, yes, twice in one problem set. Yellow grease plus H plus some water. You should know how to deal with this. When I say yellow grease, tallow, or water, let me try that again. When I say yellow grease, white grease, or tallow, this is the structure you should use. And the R group is R sub S, R sub O, R sub S. SOS, that's my little joke. And what is this? This is a triglyceride reacted with acid and water. Here's the general reaction, ester, acid, water. You get back the alcohol and the carboxylic acid you would have used to make that ester. So ester number one, I get this alcohol and I get stearic acid. As R sub S plus the carbonyl, no H, is a way of abbreviating stearic acid. If I ask you, and you should know, how to draw the structure of stearic and oleic acid, then you show the carbons. But now, for this reaction, use this abbreviation. Second ester, I get this alcohol. Notice the R is R sub O. I get oleic acid. And finally, the third ester, I get this alcohol, so I get glycerin. But once again, I get stearic acid. Being a lazy organic chemist, I'm not going to balance this. So I didn't put that tiny 2 on top, which if you want to, you can. If you don't have to. Now, important, notice when you do acid hydrolysis of yellow grease, you get three different products: glycerin, stearic acid, and oleic acid. And therefore, that's an important thing to remember. Now, if we did the same thing with tallow, use the same designation, therefore you're going to get the same products. If you did it with white grease, guess what? Use the same representation of this triglyceride and you'll get the same products. And guess what? In real life, that happens. How do I know? I worked for many years for a company that made stearic and oleic acid by doing this reaction or a similar one with yellow grease, tallow, or white grease. And our buyer, who I worked with because I was the senior scientist on the site, the buyer, he would check with me. I was also in charge of quality control. Can I buy this white grease or yellow grease? And I'd get the specifications, the analysis. I'd say, yeah, because normally we'd buy tallow, but tallow is a couple pennies more per pound than white grease or yellow grease being the cheapest. And if you're buying 150 million pounds to save 3 or 4 cents a pound, that's a lot of money. So that buyer was always trying to find yellow grease and white grease, even though there's more tallow available than the other two. But he would find it, and we'd use it interchangeably. All right, let's look at yellow grease steam. And here we have steam, which is hot water reacting with ester. And you get back the carboxylic acid, the alcohol you would have used to make that. Well, here's our designation, and here are the alcohol and the carboxylic acids. So it would be the same as F. And actually, the company I worked for, we did use steam, and we did about 2 to 3 million pounds of tallow, yellow grease, white grease per week. Yep, 2 to 3 million pounds. We had a lot of tank wagons and really a lot of railroad cars coming in, tank cars. Same thing for steam with tallow, same designation. Now, Dr. White got fancy. And here we have yellow grease, sodium hydroxide, and water. And what is that? Well, first of all, what's the designation for yellow grease? This triglyceride with R sub S, R sub O, R sub S. And now we have sodium hydroxide and water, and that's what functional group here? Triglyceride. And therefore, each one is an ester. You have the three esters, ester, sodium hydroxide, and water. Get back the alcohol plus the carboxylate anion of the carboxylic acid you would have used to make that ester. So ester number one gives me this alcohol plus sodium stearate. This ester gives me this alcohol plus, notice R sub O, sodium oleate, the carboxylate anion of the carboxylic acid I would have used to make that ester. And the final ester gives me this alcohol. So you get glycerin and you get another molecule of sodium stearate. But I just ask you give the products, and they are glycerin, sodium stearate, sodium oleate. The reason this is called saponification of an ester, because our ancestors used to take pig's fat or mainly beef fat, tallow, and yellow grease, white grease. They didn't call it that when they were settlers and things like that. And in a pot, they'd cook up some tallow, or they'd call it lard. I don't, because that's not the chemical name. With lye, lye is the old name for sodium hydroxide and water. And after a while, when they cooled down, after they cooked it a couple hours, you'd see a white solid you could pull out, which would be the sodium stearate and sodium oleate. They go like this, mold it, and you have your bar soap. All right, now, for I, use the same for yellow grease as white grease, so it'd be the same product. If I had put down tallow, it would be the same product. Now, let's look at number 6. Here's one. I think I don't know how many I forgot. I'll have to look. There are a couple, give the starting material, at least one. And here's that one. Give the starting material for the following reaction. Notice there are 3 different products. What do you react with sodium hydroxide and water to get glycerin and 2 different carboxylate anions? Think about it, alcohol, carboxylate anions. It's this reaction. And what do you start with? This triglyceride. Now, you could have written that down, or you could have written down for this one, you could write down tallow, yellow grease, or white grease. And then finally, hidden right at the very bottom, I should have spaced it a little higher. What is a surfactant? And a surfactant is a chemical. There are 2 definitions you could give that has a nonpolar tail, polar head. Another definition, it's a molecular chemical that reacts at the surface of different types of materials. And both of those would be acceptable. Any questions on the problem set? In that case, I have a question for you. I should share some of the fun. And what would be the 3 products There you go. What are the three products for that reaction? Ooh, 6 points. 2 points of product. And before I forget, I would like to wish all of you a happy Thanksgiving. I don't know if I mentioned it Monday, but I'm not going to go anywhere because I'm having an operation on Monday or tomorrow. I'm not going anywhere because I have an operation on Monday. I don't want to pick up anything from other people. The party I'd be invited to, Thanksgiving dinner, there'll be a number of little kids there who are unvaccinated because they're under 5. And I want no chance of even getting the sniffles or any chance of getting a cold. But in our family, if you go to Thanksgiving dinner, the turkey isn't the only thing that gets stuffed. We do, big time. All right, everybody done? Thank you. Let's do it. What's tallow? Well, you should know. It's this. And I'm reacting with HCl and water. Well, that's a tiny oxygen. Hold on. That's even worse. Double hold on. I tell you the day before Thanksgiving, my oxygens look awful. If you buy that, I have a bridge downtown Chicago I can sell you. But anyways, what is this? The actual reaction is this. Ester, HCl is H plus, water. You get back the alcohol plus the carboxylic acid you would have used to make that ester. So if I have 1, 2, 3 esters, ester number 1 will give me this alcohol plus this carboxylic acid, stearic acid. Ester number 2 will give me this alcohol plus, notice R sub O is the R group here, this carboxylic acid. And the final ester, ester number 3, will give me this alcohol, so I get glycerin, and I'll get another one of these. Now, for those who must, you could put a 2 there, but if you think about it, there are 3 products: glycerin, stearic acid, and oleic acid. All right, let's do something else. Let's have some more fun. What would be the product of that reaction? R sub O, carbonyl OH, that's oleic acid. And if I abbreviate it like an R sub O, you can use abbreviations too. Thank you, Megan. Thank you, Joe. Aren't you guys proud of yourself? You're learning organic chemistry and it's not painful? I hope it's not. All right, let's look at this. What is the product? Well, what does this mean? It means this. This is the structure of oleic acid. And this R sub O is this. And if I'm adding hydrogen and a catalyst, nickel, will carboxylic acid react with hydrogen and catalyst? No. But look. See, it even says it on the screen. Look. Oh, no. It's awful humor before Thanksgiving. But anyways, a double bond. And will double bond react with hydrogen and a catalyst? Remember, the catalyst can be nickel, platinum, or palladium. And the answer is yes, it will. You break the pi bond, and each carbon gets a hydrogen. So what happens here is you break carbon-carbon single bonds? No. And I have my CH3, CH2 7 times. Now I break the pi bond, and each one of these carbons gets a hydrogen. Now, if we look at this, I have 7 CH2s. Here's a CH2, 2 hydrogens. Here's 1. So it's 7 and 2 is 9, plus 7 more. I have 16 CH2s. So I can write this like this. And what is this? Stearic acid. Which, if I'm lazy, I could either write this, but I'm lazy. And you could have easily write, whoops, getting carried away with my lines here. And you could write it this way, because this right here is R sub S. And that's something you know, because I talked about hydrogenation of fats and oils. And this, if this were an ester, the R sub O in the fat and oil becomes R sub S, which is hydrogenated fats and oils. All right, now I'd like to go through a couple important things just to remind you. One is you should know. How to describe with words in a general reaction what happens when you eat, what happens in your stomach when you eat something that has a fat or oil in it. So when you eat a fat or oil, how do you describe that with words? And in your stomach, there's acid. So it's acid. There's water, and we'll call that hydrolysis. And what's the key functional group in a fat and oil? An ester. And what's the general reaction of that? And you can write it the other way or this way, like you learned for test number 3. And this is one of the important things you should know leaving my class this semester. Somebody comes up to you and taps you on the shoulder on the street and says, do you know what happens in my stomach when I eat a fat or oil? And you would be able to say, well, that's acid hydrolysis of an ester. And if you had a piece of paper handy, you could write down the general reaction right here. Now, the other thing you should know is what happens in your stomach when you eat a carbohydrate. And there, in your stomach, there's acid. and there's water, so it's acid hydrolysis. Of, and what's the functional group that holds together glucose and starches and also other, carbohydrates in general, and that's an acetal. And for test number 2, and you should know how to say with words, acid hydrolysis of an acetal, what happens in your stomach when you eat a carbohydrate, and also with a general reaction. And from test 2, and I'll write it for an acetal or ketal. If you just wanted to put H here instead of R prime, that would be fine. And we have acid, water, and you get back the ketone or aldehyde you would have used to make that acetal or ketal, plus the alcohol you would have used to make that. For those who must, let's see how tiny I can make it. Well, I made it pretty tiny then. You could put a 2 there, but you don't have to. And you should know, when you eat a carbohydrate, how do you describe with words and a general reaction what happens in your stomach to break it down? And that's acid hydrolysis of an acetal. And here the general reaction, acetal, ketal, acid, water, you get back the aldehyde or ketone plus the alcohol you would have used to make that acetal or ketal. Now, something else you should know. What's the reaction product of this equilibrium? And there, what's the key thing? I have an aldehyde, and it could have been a ketone. I have on C5, this carb right here, an alcohol. Now, in the lab, when they're separate molecules, you need an acid catalyst. When it's in the same molecule, you don't. And that's because they're connected together, they react quicker. But when they're not, you need an acid catalyst. Keep your eye on the carbonyl carbon. This attacks that, and you get what's attached to that carbon is still attached, and you get the hemiacetal or hemiketal. And in this case, this attacks here. And I showed you my way of helping you out. And I'm going to draw it down here. What's not involved in the reaction doesn't change. Profound, not really. And notice this hydroxyl group, this oxygen, is bonded to the carbonyl carbon right here, this right. So instead of teaching you how to draw Hawthorne projections, and notice that carbon also has a hydroxyl group. And you should know how to do this. If I give you the starting material and equilibrium, you should know how to get to the product. If I give you the product, the equilibrium, you should know that's glucose for this reaction and how to draw it based on going backwards. I'll give you time to write that down. I didn't mention it in the video I will post on for Monday's lecture, since I won't be here. I will go through my world famous review for the next test, test 4. I will also go through the carbohydrate problem set in that video, and I'll start some new stuff that won't be on test 4, but a few points will be on the final exam. Yep, it's coming up. Our time together is drawing to an end. Oh, that's sad. But anyways, I'm also happy you guys have really learned organic chemistry, and you should be very, very proud of yourself. I am. All right, let's do one more of these. Time out. Dr. White's got a brain freeze. That happens once in a while. When you get older, it happens more than once in a while. Yep, I knew I was wrong. I was. I'm glad I checked. All right, let's undo this structure. And try again. Now this is fructose. And I'm going to let you try this. What would be the equilibrium of product of that reaction? I'll give you a big hint. Ooh, I forgot something. Big hint. Oh, we've evolved into totally obnoxious humor the day before Thanksgiving. And when you're done, give me a thumbs up. Thank you, Joe. Thank you, Megan. All right, let's take a look at this. What do we have? Fructose. We have a ketone right here. And what do we have here at C5, this carbon? We have an alcohol. And the big hint, ketone or aldehyde, alcohol, when it's intermolecular, not in the same molecule, you need an acid catalyst. When it's intramolecular, in the same molecule, you don't need that. And what happens? This attacks that to give this product. So this is going to attack that carbonyl carbon. and what's not involved in the reaction won't change. And that's what's not changing. Now, this oxygen right here is now this oxygen bonded to what the carbonyl carbon was, this right here. So it's bonded. And what else is on that carbon? Hydroxyl group. And you should know how to do that. Or if I give you this, you should be able to either draw this, or maybe if I'm in a really nice mood, have you write down fructose. And that you should know. Now, next time you wash your hands, and hopefully you do that frequently, especially with the pandemic, you should know the following. And you should know the structure of soap in general. Has a nonpolar tail and a polar head. And the key to this whole thing, how does soap work, is, and I'm going to go to a better color. Did you guess what my favorite color is? This is the key to the whole puzzle, how soap works. Light dissolves light. And you use water, which is polar. You're trying to get rid of dirt or grease. In fact, in a commercial, I saw someone, oh, our product cleans dirty grease. All right, I didn't know there was a clean grease out there. But anyways, these are non-polar. And because light dissolves light, you're not going to get dirt or grease off your hand or whatever with water. So what do you use? Use soap. And if I blow up a little piece of dirt on your hand or mine, and I use soap and water, water will look at dirt and say, ah, you're non-polar, I'm polar, I know light dissolves light, I ain't gonna do anything with you. And it doesn't. But with the soap, the non-polar tail is attached to the dirt particle. The polar head wants to stay as far away. And when this happens, you should know this is a micelle. And once water sees the micelle, all it sees is the outer polar heads because the dirt is totally surrounded. And that's what makes up the micelle. And now water says to the micelle, oh, micelle, you're polar, I'm polar. I know light dissolves light, so let's go down the drain together. And they do. And that's how soap works. All right, this would be a good time to take a break. Everybody come back in 5 minutes. By my clock, that's 1:51, and we'll have our lab. And you'll get out of here by midnight. No, a lot earlier. I'll see you in 5. Let's get started. All right, it's lab time. It's sort of sad for me because this is a fun lab to do in the lab, but at the same time, I'd rather us be safe like this and not have to go to ECC and, God forbid, get COVID or anything else right now. So that was my call, and I made it, and I could, and I did. All right, this whole semester, you've been doing labs that I wrote, and if we were face to face, I'd be saying the same thing, where you observe things, some of the basic color tests or visual tests for functional groups. You learned about the physical nature of different organic molecules in functional groups. And I came to this point in this semester, I was thinking, well, I don't know if I did, but I was thinking, all right, how can I do something fun in a lab, and have that lab be extremely educational and teach something I haven't taught before. Hold on, I gotta blow my nose. Sorry about that. But anyways, how can it be educational and how can it be real inexpensive? And I was thinking, well, where are you an expert in? Surfactants, surface active agents. And what could be something I could teach the students that I haven't taught this whole semester that I know, and it would be good to learn. And that is the real world of chemistry. How can I do that? Well, I was a senior research and development manager and at a couple of international chemical companies that I worked for. My job was to work with marketing and sales groups and the VP, Vice President of Marketing and Sales, to develop new products to help make money. When you work for a company, that's what you're there for. A lot of chemists don't realize that, but you're there not to do exciting chemistry, which you can. You're there to help make money. And a lot of times I will have, when I was working in those positions, either the VP of marketing and sales or the head of marketing or head of sales would come to me and say, guess what? Our competitor is making this product and we don't have anything like it. We need to, because they're making a lot of money and we'd like some of that. And so my job was to, with the research group that reported to me, was develop a competitive product. Now in the real world, some of the products, and I won't tell you how, it's a secret, we can get our hands on our competitor's product and analyze it and find out what's in there. But at the other time, you have to know about things and come up with new products. So today, if we're face to face, we're not in a lab, but you're all now my research group. And the president of the company sometimes, or the VP of marketing and sales, just called me and said, we need to come up with a competitive product that this company is making and we don't. And they're making a lot of money. What's that product? What is it? It's Miracle Super. So what is it? Super Miracle Bubbles. If we were face to face, I'm not going to do it in my office. I'd take the wand out, and the hardest part of the lab for me, I'd blow some bubbles. But we've been asked to come up with new formulations for Super Miracle Bubble, or bubbles, the 100 float ounce container. In the lab, each of you would get smaller ones to work with. Now, when you're developing a competitive product, the first thing you have to do is what makes this product good? And you have what's called benchmark tests. And that's tests where you get a value or results, and your new product has to be as good as the benchmark results or better. Because if it isn't, nobody's going to buy your product. Well, that's what today's lab is. Now, let's take a look at it. Now, like I said, a key role is to develop competitive products. And we use this for various things, understanding functional groups, knowledge of patent literature. Patent literature means the patents. I can show you now. Let's do this. The most useful site other than Google on the internet for me personally is this site, uspto.gov, which is the United States Patent and Trademark Office. And until about 95, which is not that long ago, I'm looking for a word. I hide my bottle of water, but I'll get it in a second. That's when they put patents online. You could search for them. And they've done a good job of upgrading the website. If you look over here, quick link, patents, and if I scroll down, I usually don't go this way. Let me do something real quick, because the way I normally go to the site, go to Google, see where it says search for patents, brings up this page, and full patents, full text database. Click on that and see where it says advanced search. This here will never be on a test. And here, I know how to use this. Here are different fields you can do. I can put in IN name. I can spell my last name. IS, inventor state, Illinois. I'll put in the word quaternary and I'll click on search. Let's see how busy they are. And right now, it's searching on the USPTO. Oh, here's one. Method for the manufacture of polyisocyanurate, which is like a urethane foam. I'll click on that. And there's white Kenneth B with Bill Largent. And this is one of my patents. And this protects the intellectual property. But if I want to learn about things, I can learn about things that like this. If we were to go back, I can put a lot of things like, oh, here's an interesting one. I've never done this. Let's see what comes up. Uh, 1,143 patents and air bubble forming apparatus. I have down there toy. And sometimes when you do a search, you don't use the right terms. But if I come back here, if you have more than one word you're searching for, these aren't all chemical, but mostly what I search for is chemical, you can get a lot of information. And there are 3,402 patents that deal with baseball bats. Amazing. But anyways, the USPTO gives you information. And that helps you when you're starting. That's not what I want. That's what I want. In this lab, you're going to be developing and testing different formulations of bubble making solution. The goal is to make a bubble that lasts as long as a commercial product. I had to come up with, when you're in surfactants, certain measurements, the instruments to make those measurements cost tens, $20,000. And ECC is sure not going to spend that money. Now, when you do research, one of the most important things is change one variable at a time when you're doing experiments. Change one variable at a time when you're doing experiments. And a lot of chemists don't follow that. So something worked and you change two things, which causes it to work. Or if something doesn't work and you change two things, well, both of those, was that the reason? Or just one of those things that you changed, was that the reason? And that's why you only change one variable at a time. Now, at the same time, I'm using a lot of time today. It's real bad humor before Thanksgiving Wednesday. But anyways, to save time, and time is money, research scientists have come up with what's called DOE, Design of Experiments. And this is a way of setting up a grid of different experiments where between each experiment, you change only one variable at a time, but overall, you do a lot of variables very quickly. And Dr. White, me, knows quite well how to do DOE. So I've set that up for you for this lab. Now, what's the main thing we're dealing with? That's not what I want. I thought I had it here. Hold on one second.
Grammarly can't teach you to dance, but it can help.
All right, thumbs up, people. You see YouTube on your screen? Thank you. If you look, there are kids and a machine blowing bubbles. That looks like a lot of fun. Oh, I like one of those. Oh, is that Finding Nemo, I think, or something like that? But see how it's blowing the bubbles? And let's look at this little kid, and that's how you blow bubbles. And in the lab, you'd have a bottle like that, a little smaller, and you'd be able to blow bubbles like that. And notice it's a lot of fun. This is a lot of fun lab. And the question is, what's a bubble? I bet you never thought about what is a bubble. Well, let's take a look. Now, a bubble, I'm going to magnify it. On the outside of the bubble, by the way, this is my bubble. The outside, we have air. In the inside of your bubble, guess what? We have air. And surrounding it right here, you have a solution. And that solution contains water and surfactant, or maybe more than one surfactant and other chemicals. Now, water, we know, is the major component of bubble solution, which is why it's so profitable, and it is, because I found one time, I didn't do it just now, about over 100 patents, probably 150 patents on making bubble solution. It costs a lot of money to file and get a patent. Figure just the legal fees and the government fees, we're talking about $30,000, $40,000. And then to pay people like me to do the research is even more money. So if you get a patent, you figure I'm going to make a lot of money with something, or you're really dumb, and companies aren't dumb. They don't do that unless they think they're going to make money. So we know water is polar. And air, which is nitrogen, oxygen, is nonpolar. And what this means is the surfactant or surfactants form a micelle. A bubble is really a micelle with air in the center and outside. And it was different from the one with soap. Here, the polar end, and let me magnify this. Here's the air. Yeah, the polar end, non-polar tail wanted to be near the air, and the polar end of the surfactant wanting to be inside the bubble, the liquid. And same thing on this side to the outside air. I'm only going to draw two of them, but it's a whole 360 degrees. And this connection right here helps keep the water together around the air. And the bubble is just a micelle. So what are we going to use to test to make our own products? Different surfactants. And what are those different surfactants? It's going to be dishwashing soap, which is Dawn. That's the best product out there. And this would be, I think in the lab, we use Dial liquid soap. And the laundry detergent, my favorite, All. These are all surfactants. Now, if you look at the patent literature, companies have found if you put certain things in with a surfactant, it makes better bubbles. And one of those things is glycerin, that helps hydrogen bond it, and corn syrup, which is mainly fructose, a lot of hydrogens. And later on, I found instead of corn syrup, it was easier to use starch solution, which is similar to corn syrup. And you don't know, will this help or not? You've got to go in the lab and test it. Now, before I go any further, let's look at something you need to know. For Dawn, your dishwashing, solution or product, you have an R group about 9 to 12 carbons, oxygen, then, oh wait, CH2, then oxygen, and the sulfate anion. So you have a polar, non-polar tail, and here you have a polar head. Next, if we look at the liquid hand soap, like in the key surfactant is similar. R group, CH2, CH2, and on to CH3, 9 to 12. And here you have this OCH2, CH2 repeating n times, where n is equal to 3 to 5. And then you have the same sulfate anion head. This is called usually sodium lauryl sulfate, sodium laureth sulfate. They're similar but different. The second one, this molecule, is milder on your skin, which if I'm washing my hands, I'd like it to be mild. And again, here you have the nonpolar tail. And the polar head. And the last one is all laundry detergent. And here it's a little different. Again, RC9 to 12, I forgot the exact length right now. You have a benzene ring. And now you have a similar, but a little different sulfate anion. And here you have your nonpolar tail and your polar head. And these are the 3 surfactants you'll be using. Now, in each of those products, there are other chemicals that help make them work well in whatever application, like all in your washing machine, Dawn in your kitchen sink, and liquid hand soap to clean your hands, and I guess your bathroom sink. Now, in part A, you'll be testing the Dawn dishwashing. And I've already made up formulations. And in the real life, when we were face to face, you would be making up these 5 formulations and testing them. How do you do this? You mix it in a beaker, you take the wand I give you, and you blow some bubbles. And you take the average of 5 bubbles, how long before they pop? And there, you don't need expensive equipment. In the lab, we have a clock with a second hand, or you can use the old favorite 1001, 1002 to count. Now, A1 is 2 milliliters of the dishwashing soap and 18 milliliters of water. Oh, one good thing about this lab is you can try this at home. And A2 is 4 milliliters of the dishwashing, 16. And effectively going from A1 to A2, we've doubled the amount of surfactant. Now in A3 and A4, we're going to be adding glycerin. In A3, we're using a formulation A1, what's left over, and add 5 drops of glycerin, test it. In A4, we're going to use all of what's left over from A2, the higher concentration, and we're going to put a lot more glycerin. Again, each one of these is setting up a design of experiment, DOE, changing one variable at a time. Even though overall it looks like a lot, it isn't. And finally, A5, because students run out of A2 by this time, you put the glycerin in it, you'll make another A2 and now add 10 drops of cornstarch, which is the same effect as fructose, but it's easier, I found, to have students deal with that instead of the fructose. And what do? You test it. And this is the average of 5 bubbles. Now, the benchmark is the commercial. If you test the commercial product, the Miracle Super Bubble solution that I showed you earlier, you get a lifetime average of 10 seconds. And here we have different formulations, the A1 through 5, and how long it takes. Now, one thing I tell the students is if you do try 10 times, no bubble, but you can pretend there's one, and you get no bubbles, put down 0. That could happen. When you're testing things, some of your formulations awful, and some are really good. And that's why you do research. Now, I also tell students, one, it's not polite to blow bubbles at your other classmates and especially at the instructor. And more importantly, it's not polite to pop your neighbor's bubbles. I had one student do that the second time we did this lab. I had to stop him. That's not nice. And the other thing I warn students, when you're blowing bubbles in the lab, we have a linoleum floor. Wipe it up every once in a while with paper towels because it gets slippery. They're surfactants. Now we do the same thing, but now the change in variable from part A to part B is a different surfactant. Instead of using the Dawn dishwashing, we're now using the liquid hand soap. And in the lab, we use dial. And you also add glycerin and corn. So it's the same setup, but the difference is the surfactant. B1 is similar to A1, B2 is similar to A2, B3 is similar to A3, and look out, it's a bad joke coming. And before what? I can't resist saying that, I didn't. It's the same as A4, and B5 is the same as A. The only difference is the change in surfactant. Now, one thing, the liquid hand soap we use is very viscous, thick, and it's hard to measure out volume, so that's why it's changed to weight. And you do these 5 formulations and test them, blow bubbles. And here are the results. Now, when you're doing this in real life in a lab book that you keep in a company that's signed once a week by someone else, and you have to sign it and date it every day, we have what's called the commercial product, and you don't have to do it again. You just copy the same number from table A. That's real life. And here are the various values for B. And finally, in part C, you will be testing the efficacy, how well it works, the laundry detergent all. And you'll make the same formulations as we did in the others, C1, C2, C3, C4, C5. The only difference between this and table A or B is the surfactant. Everything else stays the same. Again, setting up a very complex, it's called an array or DOA, design of experiments, where I can get a lot of data very quickly, but really each experiment, we're only changing one variable at a time. And think of it as like a 3-dimensional chessboard, if you've ever played that, or tic-tac-toe. Tic-tac-toe we did when we were kids, but not this. But anyways, and here are the results. Now, if you have 10 tries and you get no bubble, you put down a 0. Uh-oh, there are a lot of zeros there. And then a number of years ago, one of the students came up to me because I just did part A, B, C, and I had the student said, "Can I try my own formulation?" I said, "That's a great idea. Go for it. Just use the chemicals we have set out in the lab, the glycerin, cornstarch, and the different all and hand soap and Dawn." And they came up with some great bubbles. And I had one semester, I think it was 3 years ago. It was the perfect storm, so to speak. And the student, she blew a bubble and went up near the ceiling, and it lasted almost over 5 minutes. And after a minute or two, the whole class would stop what they were doing, just watching that bubble. It was awesome. And when it popped, everybody said, now, one of the things I do is to give you that real world experience. If you were in my research group and you came into my office and said, Dr. White, we got the formulation, I found it. Let's tell everybody. I said, whoa, wait a second. Before we issue an announcement or report, which I'm going to sign off on, literally you do that in chemical companies, you're going to show me it works. I'm the boss. Show me it works before I stick my neck out. And I've known bosses who didn't, and they got in trouble big time. It never happened to me, because first show me, and then I'll sign off. And when the big boss is watching, things get harder. And in this lab, when we do it face to face, I have each student, all they have to do is blow 2 bubbles with whatever formulation, theirs or mine, that they think is the best. And it gets interesting, fun, really, because they're under pressure. And to show that, I actually asked the students, once you blow your 2 bubbles, I have a place where I initial it. I put it in for this lab. Now, before I finish, there's some things I need to talk about. One is there's certain chemicals that make bubbles, and we call them, the chemical industry, foamers. And they also put foamers in some of the products you buy. Dawn has a foamer in it. You've been conditioned that bubbles, foam, makes things clean. No, it doesn't. It's the other surfactants, but you've been conditioned, ooh, this makes a better foam, it's a better product. That just tells you there's some surfactants in there that will make foam. Now, there are products that are foamers, make foam, surfactants. There are other surfactants that are called defoamers. They destroy or stop foam from happening. And when I was working at one company, because I was a senior scientist where we had a research, and there was also a chemical plant, we had these 2 waste treatment ponds that any of our chemical waste, before it was entered the city sewers, had to be treated. And one of the ponds had an active colony, microbes that eat up. Had our waste was fat and oil and some other company stuff. And somehow one time, all of a sudden, that pond, there was foam growing. And this pond is the size of a football field, about 30 feet deep. I think I calculated it was over 1 million gallons of liquid and other stuff in there. It had 4 great aerators, looked like propellers, that kept oxygen going into the water like you do in an aquarium to keep the microbes in there that were eating up the stuff. Well, anyways, there's foam, and this pond was about 100 yards from 47th and Racine in Chicago. And if that foam hit the street, they'd have to close it down, and we'd be fined a lot of money. So the president said, it's your job, get rid of that foam. I finally found a defoamer that worked, and there was none in the Chicagoland area. The company paid, I didn't, a lot of money to charter a plane. Yes, charter a plane to deliver 4 barrels. That's about 250 gallons of this defoamer to put in 1 million gallons of liquid. And we did it, knocked it down. President was happy. I was relieved. So there's foamers and defoamers. Now, another thing you should know is that in chemical companies, when we sell chemicals, we have what's known as a sample room. And a sample room is a place where if a salesman or marketing manager wants to give a customer samples to test our products and their new products, we ship them out free of charge. And samples can be anywhere from 4 ounces up to 5 gallons, a couple of 5-gallon pails. One company sent me samples. I said, I just want a little bit. And the salesman got all excited because I was with a major international company. And my position, he knew from past experience, I get new products out the door. And he sent me 4 5-gallon buckets of this chemical. I only needed a couple ounces for my research people to test. Didn't work out, and we had to get rid of those, all that. But anyways, sample room sent out samples. If you're in a big company, you call them up, the company up and say, hey, I'm looking at to test, I want to try this product. Can you send me a sample? And if you're at a big company, you have the credentials, which I did, they do like that. Anyways, when it comes to samples and chemicals, there's 2 types you should know of in the real world. One is industrial chemicals, which I worked in, and the other is food grade chemicals. And food grade chemicals are not only very high purity chemically, they're high purity biologically. In other words, they don't have any nasty things in there that will get you sick. So you can use that if you're using it in food that's going to be consumed. Well, when I worked at one company, I joined it. This is a funny story. I think you'll enjoy it. Right before Thanksgiving, I worked for a company, and it was, I won't tell the name. But anyways, before I started there, hold on one second. Got to be careful with that. But anyways, before I started, the managers had this thing where every Friday after work, all the senior research development managers would go to this, you might want to call it a bar, this hole in the wall place. They had some tables, a bar, no window, sort of dark, and they'd get some beers and they'd talk about the week, how stupid some of their employees were, how stupid some senior management were, and just get off some grief off and, blow off some steam from the week. And it was fun, and I went. Well, it turned out the owner of this bar had a unique talent. When you ordered a pitcher of beer that he pulled from a tap, he found a way he could put 1/3 of that would be foam. And if you didn't like it, someone complained, well, go somewhere else. And he was pretty, not rude, but close to it. Well, I wish I could say I did this. I did. No, I wish I could. But one of the other managers who also knew surfactants like me was getting really mad about this. And he didn't tell anybody, but he was really getting teed off about buying all that foam. When we were at that get together, we all pitched in, but anyways. So without telling anybody, remember I told you there are surfactants that make foam and defoamers, surfactants that stop foam. Well, he got a sample of food grade defoamer, and he, in a little squeeze bottle, plastic bottle with a little dropper tip, he put in that food grade defoamer, which is safe to consume. That's why it's food grade. And we went to that bar, and when the bar owner wasn't looking, it was pretty empty that Friday afternoon. Said, tell me if he's looking. He took out of his suit pocket bottle and the almost empty pitcher. He put in a whole bunch of surfactant, mixed it around, say, hey, we need another pitcher. If you've ever been in certain bars, they have for pitchers only, not glasses, they have a soap sink, then a rinse sink, and they put it up. Well, after 2 or 3 pitchers, that soap sink and the rinse sink were contaminated with defoamer. We stayed later that day than usual. And all of a sudden, the owner couldn't put a foam on that pitcher of beer. He was giving us more beer. He wasn't happy, and we were watching him get mad, and we started laughing. Finally put 2 and 2 together and figured out, you guys are scientists. What'd you do? We didn't do anything. We didn't do anything. He said, get out of here, never come back. And we did. And we found another place that didn't sell us all that foam. So remember, there's foamers and defoamers. Now, if we were in lab today, I would point out while I was walking around, everybody would get really concerned how come for the part C, which used the laundry detergent, we didn't get any bubbles? Well, think about, where do you use that? In a laundry machine, or your laundry machine, and you don't want any bubbles forming there. Now, over the years, I've had more than one student tell me either they or a friend, ran out of laundry detergent for the washer, clothes washer, a laundry machine, clothes washer, and they used, are you ready for this? The Dawn dishwashing. And you know what happened? This has a real good foamer. Their whole basement was covered in foam that was coming out of their washing machine. So anyways, I thought I'd tell you, and that's a true story about with the bar. And with that, I'm done. I'll see you a week from today, because remember, next Monday, I'm having this eye taken care of. So I don't need a lens. I won't need glasses, other than maybe for computer stuff. I will. My eye surgeon warned me about that. And with that, you have a happy and healthy Thanksgiving. I hope you get stuffed just like the turkey and enjoy every bit of it. And with that, I'll say, gehen gesund. And tonight, if you need, I'm going to, for an hour from 5 to 6, I'll have my office hour. I don't have to, because technically the school's closed, but that's a special service I'm doing for you, from me. And with that, I'll say bye now. Gehen gesund.